Today is October 17th, 2021, and my guest is astronomer Sandra Faber of the University of California, Santa Cruz. We're going to have a conversation about humanity. We're going to go back about 14 billion years, and we're going to go forward about 1 million years, so hold on to your hats. Sandra's field is the formation of galaxies. She's published hundreds of scientific papers. She's won a lot of awards, medals, prizes, delivered many named lectures, a bunch of honorary degrees. She's an extraordinarily successful academic astronomer. And we connected, the two of us, because Sandra's interested in the question of what would the economy 1 million years from now be like? And she and I had the beginning of a conversation about that. We're going to continue that here. And we're going to talk about what an economist thinks about that question, which I think will be maybe amusing and fun. And we're going to start with a little bit of astronomy. So, Sandy, let's get started. Now, you have suggested to me, and I suspect elsewhere, that astronomy is kind of expensive. How expensive is it?
A few years ago, by the way, Russ should say how glad I am to be here and really looking forward to this wonderful conversation. As to your question, a few years ago, I estimated that the typical PhD from our department, if we were completely honest about it, and tried to incorporate and include all the things that went into supporting that student, including the expensive telescopes that they used, was $500,000.
For one?
Mm-hmm.
To train a PhD?
That's right.
And that's a lot of money. Where's that come from right now?
It depends on who you work for. I work for a public institution, so it all comes from taxpayers, basically. So my dad used to tell me constantly, this is the refrain I remember from childhood, Sandra, make yourself useful. So in my later years, I imagined having a cocktail party and needing a ready answer to a skeptic asking me, why the heck should we support you people? And simply out of a sense of self-preservation and aggrandizement, I began to ruminate on the worth of astronomy to the human race. Now, roughly half the people I meet are intrinsically interested in these questions. But that wasn't enough for me because roughly half the people are interested in the Beethoven Symphony. And I didn't really want to think that astronomy was sort of just an aesthetic endeavor. I wanted to think that it actually had some much more practical applications. So that's what I've been thinking about. And coming to the conclusion that astronomy actually is very important because, especially at this moment, because the human race is at a juncture, as so many people say. What we're doing for the first time here really influences future generations. And to plan and to have a sense of values. I hope our conversation gets onto the subject of values later. We need to have a story. And astronomy tells us the first chapters of the story, the beginning of the Big Bang, how we got here. Then the geologists take over and tell us about the history of Earth. Biologists tell us about the origin of life and so on. These three sciences, put them together, they tell us who we are, how we got here. And that's the foundational knowledge we need for thinking about where we're going.
So I'm a big fan of all three of those things. I'm in that half that's interested in these questions deeply. I think an educated human being, unlike an animal, should have some idea of where we've been. Just forget about the practical idea that it might help us about where we're going, but certainly about where we've been. And on some recent episodes, we've had some question of whether the examined life is worth living. To me, if it is, if the examining part is important, certainly what astronomers have taught us over the last few hundred years is rather extraordinary. It is aesthetically very pleasing, and it's not cheap to put on a performance of a Beethoven symphony either, by the way. We have to be right honest about that. There's a lot of training, a lot of hours, a lot of opportunity costs, as we say in economics, things the musicians could have done otherwise, and the conductor, the space that the hall is in, and so on. So when we think about the practical side, there's some practical sides to astronomy that are extremely valuable.
Yeah.
Like an asteroid's about to hit the Earth. We'd like to know when, right? Those kind of things.
I'd like to start with something even more basic.
Okay.
So I think maybe we'll touch on this later and how astronomy relates to religion. But the point is that astronomy tells us, together with these other sciences, I don't mean to think that astronomers answer all questions. We have put forward a story that doesn't have any miracles. It doesn't have any supernatural inputs. This is the most profound message. We live or die by the laws of physics. We are prisoners of the laws of physics. And no supplications, no hopes, no dreams, misplaced trusts are going to solve that problem. So if we're confronting issues, as I think we are on Earth, the first thing we have to keep in mind is that we are limited by the laws of physics. And that has many implications, but that, above all, is the most important lesson.
Yeah, I don't know if you know, I'm a religious person, and I think I saw one of your talks where you talked about how the way you phrased what you just said was that science was the end of magical thinking, which is another way of capturing this idea that we're constrained by the laws of physics, the reality, what we might call reality, that we can't hope for a miracle. But I have to say, when I look at modern astronomy and physics, there's maybe you don't want to call it magical thinking, but it's very different than this experimentally based approach that has been the dominant successful aspect of these sciences over the last going back to Francis Bacon, I guess, if you really wanted to be fair about it. So maybe we'll come to that. So, but I accept the point that are you looking at me like I'm crazy? You want to say something,
Yeah,
Sandy?
you can see I have a very puzzled expression, so I'm looking forward to that topic.
Well, let me just say one thing about it. I'm thinking about the multiverse. I'm thinking about string theory, things that are highly speculative, not as grounded in empirical science as other parts of our understanding of the cosmos. That's all. That's one thing I meant. The other thing I meant is that, that first 10 to the minus 43rd of creation that we can't see, and then the 10 to the minus 35th where things get a little more normal, and then we get about 3 minutes in, and then it's just smooth sailing, sort of. There's a lot of, I'm not going to, magical's to dismiss it, but I don't know how firm our knowledge is of all these things. We have a lot of confirmation, though, which is extraordinary, right? I mean, when I think about your field, let me say it this way, and then you can react. For a long time, what astronomy was curious people looking through a tube with some glass in it. And you could argue that's still kind of what it is, but what we've been able to do with the fact that we weren't around 14 billion years ago, and yet we seem to have quite a bit of knowledge of how we got here from there. That, I think, is one of the great triumphs of the human imagination and human creativity. And for me, that's part of the reason it's worth paying something for. Maybe not $500,000 per PhD, and maybe not many more going forward, but certainly it's been an extraordinary run.
Well, you've sounded another theme. This is why I think astronomical training is really valuable. We are training more graduate students and PhDs than can be absorbed by the field. And more our students are going into other lines of endeavor, which I think is wonderful because I believe that astronomical training has some aspects that are unusual. And first of all, there's a grasp of statistics, which most people don't have. Second, astronomers always have imperfect knowledge, but try to come to conclusions anyway. And so we're not paralyzed by the fact that we don't know everything about something before trying to generate a hypothesis. And this is useful for policymakers and planners on Earth today who need to react, need to make decisions without complete knowledge. So the astronomical state of mind sort of prepares you to do things like that. But the last point you just mentioned, and that is the knowledge that things change and change profoundly. And therefore, the ability to imagine a world, a universe, a system, which is totally different from what you see today. You see, I think most people, and to some extent myself included, we're trapped in a small space of time. People often say, well, human beings are so small, thinking that, we're physically small or we don't control that much energy compared to the universe. That's not our problem. The main limitation we have that keeps us from thriving better in the universe is having short lifetimes compared to the time spans on which other important things are changing. And you're born into a society as a child. You are taught that this is the way things are. You're taught a little bit of history, but it's sort of peripheral. And evolutionary trends encourage you to adapt to that moment as you're growing up. And we're all of us kind of trapped in our childhood moments. And that's the problem in planning the Earth's future over long time scales, or even, a few decades now, because things are moving so rapidly. So I think astronomers bring a new perspective to the table that's useful. And maybe I'm just really speaking of myself, because that's why I'm coming to the table now. It's really driven by my cosmic interests and perspective.
And we're going to go into that in a little bit of depth, but I first want you to talk about something that surprised me when we talked before off the air, and that I've seen you talk about in some of your online talks. When I was growing up, we were told, well, we've never seen another planet. So it's possible, because we couldn't reach it with our telescopes. We weren't sure there were other planets. We weren't sure what their quality was for sustaining life. But then there came a view, for a lot of reasons. Actually, there's tons of them. there's 10 to the 22nd stars. Many of them have planets. So there's nothing unusual about the Earth. And you've said that actually that's not quite perhaps true. So tell us what we know, at least now, about the ability of life to be sustained outside of the Earth on, say, in other parts of the universe.
Well, first of all, I think when you said we'd never seen another planet, you meant an extrasolar planet, an exoplanet.
Correct. Sorry.
Yeah.
Yes.
Oh,
outside,
right.
Outside of our solar system.
Yeah. Okay. So yes, you're correct. There's been multiple ways of discovering them, and one particular space mission, in particular the Kepler telescope, discovered thousands of them. Yes. So you ask, what do astronomers think about whether Earth is rare or common? Now, implicit in that question is, what is an Earth? And that's the answer to the question hinges completely on the answer to that. So I think implicitly, when people ask this question, they have Earth as we know it. And Earth as we know it as a haven for life. What we don't understand is whether we could change Earth somewhat in different ways and still have intelligent life. I think what we're really interested in is whether intelligent life can thrive all over the universe, or whether only in extremely limited areas like Earth. So there are two schools of thought. One school puts together an equation with a small number of factors, multiplies by the number of eligible stars, and comes to the conclusion that there are suitable planets everywhere. Another school of thought, called the rare Earth hypothesis, puts in more factors and it doesn't take that many more factors before you conclude that Earth really is incredibly rare. In my talk that you're mentioning, I wrote down 17 different factors. I don't think anybody has ever tried to write that many before. So this is, maybe we'll call this the Faber equation. And if you said that each factor reduces the chances of having an Earth-like planet that can support intelligent life by a factor of 10, i.e. each factor is 1/10, 17, 10 to the minus 17. How small is that number? Well, there are 100 billion stars. That's 10 to the 11th stars in the galaxy. 10 to the minus 17 times 10 to the 11 is a very small number. It's 1 in a million. Yeah. You could very well persuade yourself that Earth is the only planet of its type in the galaxy. I've already persuaded myself of that, but other astronomers, I'm sort of out on a limb. I don't think it's generally agreed to.
That does kind of blow my mind. I mean, the Milky Way, if you've ever seen it at night, if you've been lucky enough to see it or in a photograph, you get a pretty good idea. It's got a lot of stars. The idea that there's not one of those stars that has an Earth-like planet in terms of carbon. I mean, temperature is temperature the main thing? What's the most of the 17? What are some of the factors?
Probably the most important is a temperature that supports liquid water on the surface. It's called the habitable zone. That's where people started. But there are a lot more factors there. For example, we here at Santa Cruz just wrote a paper on the magnetic field of the Earth. And that is necessary because the sun is putting out energetic particles all the time, which, if unopposed or allowed to impact the atmosphere, would ablate the atmosphere and would also be energetically unfavorable to life on the surface. So somehow you have to protect ourselves from the solar wind and solar flares. And the way we do that is something called the Magnetosphere, which is a region of space where the Earth's magnetic field energy dominates over the solar wind and deflects it. What does it take to make a magnetosphere? You need a liquid iron core, and you need a proper structure of the planet in which the core can't cool off too fast. And that means that the covering has to be sort of hot for longer than you would think. How does the covering, the mantle, stay hot? It stays that way through radioactivity. You have to have the right amount of radioactive heating in the Earth's mantle. But if you have too much, you have volcanism. And volcanism is probably the greatest long-term enemy of intelligent life on the surface of Earth right now. Not asteroids, maybe, but volcanism. It turns out that there's a window of plus or minus a factor of 2 either way. And as we look at other stars in the galaxy, we can see that their amounts of radioactive elements, uranium and thorium, aren't right. So there's another one that's at least another 0.1, 1/10 factor in my equation. It was number 17 in the equation.
But there's 100 billion stars approximately.
Yeah.
I should, long-time listeners will know, I want to say, well, it's really about 100,384,760. Anyway, precision is not really relevant here, but the Milky Way is only one of maybe 100 billion galaxies, which is, of course, a crude estimate, but probably in the ballpark. So there's lots of other places there could be Earth-like things.
Yes. So let's pursue this game of multiplying by powers of 10. So you're right. 10 to the 11 stars in the galaxy, 10 to the 11 galaxies in the visible universe, 10 to the 22 times 10 to the minus 17, 10 to the 5. Okay? What's 10 to the 5? That's 100,000 Earth-like planets in the visible universe. How are you going to get to them? I mean, they're dispersed over enormous space. It's effectively zero, even though it's not zero quite.
So I was talking to a physicist about what you had told me before, and you had suggested to me we probably won't be able to leave the galaxy as human beings. We might be able to leave the solar system, but not the galaxy. Why is that?
Just distances are too large. Yeah. So it's this lifetime problem. That's what's preventing us more than an energy problem from voyaging the stars. So people solve it by putting living organisms in suspended animation, and then you wake up at the other end of the trip, Well, that might work to a degree. Another way of doing it is to make a machine, which one imagines doesn't degrade. That reminds me of the Long Now Foundation here in San Francisco, who have set out to make a clock that will operate unattended for 10,000 years. It turns out that that's a very, very hard thing to do. That's because biological organisms repair themselves, but machines don't automatically repair themselves. So we have not found a solution to the time problem.
So that means that our home right now is the Earth. It might eventually be somewhere else in the galaxy, but it probably isn't outside the galaxy. I just want to raise one thing, which is just like my all-time favorite thing. Okay, not really my all-time favorite thing, but I do love it, which is that when you look up at the nighttime sky, no matter where you are, meaning whether you're in New York City, where you might see literally a handful of stars on a night, or if you're in in Hawaii and you can see or Yosemite in California, or the Negev here in Israel, you can see thousands of stars. It's magnificent. All those stars are in the Milky Way, aren't they? Except for maybe a galaxy cluster you might be able to see.
Well, we can see in the southern hemisphere the two Magellanic Clouds,
right,
which are separate galaxies, small ones. And
but individual
if you know where
stars,
to look in the northern hemisphere, you're right. Yes.
So that blows my mind. So as busy as the nighttime sky is on a cloudless night in a desolate place, you're still only seeing 100 billionth of the number of stars in the universe that could be seen if you had a different telescope than you're right.
Oh yeah,
that's really amazing. It blows my mind, especially because you can see the Milky Way, which looks like it's over there, but all these other stars that you're seeing are still part of it.
Yes.
Okay. Glad we got that straight.
Okay.
So we're stuck here. We can't, but we've got some time, right? Because talk about the sun. The sun's going to run another billion years. Is that right?
Yeah.
Long time.
A long time. Yeah. Something on that order. We lose photosynthesis. It gets too warm here to support photosynthesis. That's probably the first predictable cosmic catastrophe for us. It's on the order of several 100 million years.
So we have some time to think about if we could survive as human beings until then.
Well, let's mention two other things. First of all, there's the asteroid that you alluded to. So that's a problem we have to solve. We're now at least watching for them, but steering them away from Earth that's a technical issue that I think is not quite properly solved. Let me return to the volcanoes, because the most massive extinction on Earth was 250 million years ago, and that was caused by not explosive but lengthy volcanic eruptions. And I think we need more models of the interior of the planet. The planet is cooling. So over time, these things will become less likely, but how likely, I don't know.
When you say cooling, you mean over like a really long period of time, yes. I assume.
That's right. Mm-hmm.
When you say we're watching for them, the asteroids, who's we? Who's we? I haven't looked for one lately. I mean, is there somebody who has that job? It's a good, I'd like there to be. Is there someone?
Yeah, NASA has a program to patrol for moving asteroids.
How much advance warning would we get?
Probably depends on the size of the object. So we know where all the big objects are, but there's a range in which you can do a lot of damage, but they're also hard to see. So The last time I looked at this, we were seeing all the really big ones, but there's an intermediate range that we don't have the capability yet of seeing, although NASA's working on this. So, yeah. But then what do you do if you see it? You would have probably
Call
at
your
least,
loved
I would
ones.
think, you'd have a year to think about it.
So
Yeah.
let's play with that for a sec. When you say they're intermediate size, the bigger ones, I assume you get more warning because we know where they are already, or some idea.
Yeah.
What's the definition of a big one versus an intermediate one? Would a big one the size of a city? What are we talking about here?
Roughly, yeah. A kilometer. We know where everything is with the size of a kilometer or bigger. But a tenth of a kilometer, that's another matter. And even, 100 meters can do a lot of damage. So, yeah.
Would it do?
It's in that area.
What kind of damage would it do other than the unfortunate creatures that were under its direct attack? A lot of dust? Is that what we're worrying about?
Well, 2/3 of the Earth is water. So it's going to land in the ocean.
Most likely.
And there's going to be an incredible tsunami. That's probably the most important thing.
So what options do we have for... You're smiling. I don't know why you're smiling, Sandy. It makes me smile too, kind of. I don't know. There's a certain hopeless charm to it, I suppose. But what kind of options would we have to do something about it? We couldn't steer ourselves. Would we attack it? Try to obliterate it?
People have thought about this. You're pursuing an area that I'm not so expert on. So let me say a few words and then hope that we'll start talking about something else soon.
Okay, fair enough.
Okay, so the issue is whether you should try to, let's say you have a certain amount of energy available to transfer to this object. You have to distinguish between energy of the object, its kinetic energy, which goes as the velocity squared, versus its momentum, which is proportional to velocity, mv squared versus mv. We don't want to change the energy of the object. We want to change its momentum. We want it to go in a different direction. And it turns out, people thinking about this, that if you send a spacecraft to it with a certain amount of energy, it is better not to try to blow it up all at once, but rather to somehow use your store of energy in a series of small taps that delivers, in the end, more total momentum change to the object. So don't think about sending a nuclear bomb to explode it or something like that. That's not going to work. It's going to be something more sophisticated. It's challenging, though.
Pretty sure I saw a news story today, which I did not click on, about nuclear weapons being used against asteroids. But I think certainly for the people in the space ship, they'd certainly prefer the tapping to the nuclear bomb. So that's good all around. It's a win-win, as they say. Let's talk about entropy. What is it, and why is it important to you?
Okay, so I'm going to start with a couple sentences about why it's important in an effort to motivate people to listen through the explanation. So entropy, people have all heard about the second law, I'm sure, the second law of thermodynamics, which says that entropy can only either stay the same or increase. It can never get lower. So there are people who think that this is probably the most important law of physics and the most incontrovertible law. Maybe we'll find that our theory of gravitation, general relativity, is wrong somehow. We're still dickering around with the nature of the other three forces, etc. But somehow people believe that we will never find a contradiction to this. So this is regarded as the most inexorable, unavoidable law of physics. And I said before that we're subject to the laws of physics, so this is an important one. What is it? Well, it had its origin in the study of thermodynamics. And basically, here is a system. Let's make it simple. a bunch of atoms in a container. They have a temperature, and they're moving around. The hotter the temperature, the faster they move. Let's consider the number of ways in which we could arrange that system microscopically in order to have the same total energy content. So here is the system. It has a certain amount of entropy. Entropy is a number like energy. It's not the same. But you can calculate what that entropy is. And the number is bigger when the number of microscopic ways we can rearrange the system to have the same total energy is bigger. So consider two arrangements of gas in two different containers. One container, they're the same temperature, so the speeds of motion are the same of the molecules. But one, and they're the same number of molecules, but in one case, the container is smaller than the other. So how you can just see intuitively that the ways in which I can arrange the molecules in the bigger container is bigger because I have more space available to me to put them in. So that is why if I take the walls away from the small container, the gas will expand to fill the bigger region because the number of states available to it are larger. There's a suppressed assumption here that conditions are always, that systems have the ability to move from microstate to microstate, and that they will distribute themselves with equal probability across all the microstates. And so if a system has more microstates available to it, it will take that configuration.
By microstate, you just mean possible arrangements of the molecules, right?
Many people, economists included, are now thinking that there are laws of entropy that would apply to society just as they would apply to particles, say, in a gas or the particles in an expanding universe. Let me give you an example, okay? Things get messy. It's hard to keep things ordered. So the analogy here would be the refrigerator. How do I make an area that is cold if entropy just wants to have heat flow and the temperature even out? You know, it's very hard to make things cold. You have to build a machine. You have to put energy into it. And it takes work in a refrigerator in order to move heat from the contents to the surrounding kitchen. What have we done? We've cooled the material inside the refrigerator. That is lowering its entropy. And it took work and effort to do so. Consider a parent trying to get a child to clean up its room. Rooms get messy. One of the reasons they get messy, the reason is that there are so many ways they can get messy. There's only one way in which a room can be ordered, right? So the laws of entropy tell us that it is very improbable that a room be ordered. It's going to find its way into these other much more probable states, and there are many of them. So the parent must intervene. That takes energy, it takes effort. The parent had to eat dinner in order to be able to stand in the room and browbeat the child, et cetera, right? So now here's a very interesting thing that I'm beginning to worry about. The refrigerator took work in order to cool, and it had to have a reservoir to put the waste heat, which was the surrounding kitchen. We didn't mind because the reservoir was big. What if human society is governed by the laws of entropy and it takes work, which is energy, we're all eating and metabolizing, that provides the work. But where is the waste? Is there waste heat? And where is it going? And is this one of the limitations that will govern the evolution of intelligent life on Earth? So let me give you an example of the waste heat that we have in mind, right? So one of the ways in which the economy increases entropy is it mines ore. So ore deposits are very organized. They're not dispersed. If I took all the silver in the world and spread it out uniformly over the surface of the Earth, I couldn't use it. The only reason I can use it is in lumps, and I can access it because it's a low entropy resource. So this is what people mean by the circular economy. If I keep mining silver over the years, what happens to the waste silver? It goes into landfills, or in some way it's dispersed in a way that's not usable anymore. Every resource that we are using like that is an exhaustible resource. And we should think about not mining ores and things like that, but as mining low entropy and therefore extremely valuable assets.
Well, we're going to come back to that fairly shortly, I have a feeling, but in our conversation. But I wanted you to talk about how you saw entropy and the fight to reduce entropy as central to the human project. Because you told me off air that you saw the fight against entropy to be part of a central piece of human meaning and purposefulness.
To stay alive, you have to reduce entropy. This is what biological organisms do. So let's it's very interesting. We are simultaneously refrigerators and power plants in our bodies. So on the one hand, we're refrigerators because we are creating greater organization. We are lowering the entropy of our atoms to create new versions of DNA. Whenever our cells divide, we have to create very, very ordered strands of DNA in the new cells. How are we doing that? We're ingesting things that aren't DNA, that are much more disordered. Somehow we have to create order out of disorder, and that's a refrigerator to my way of thinking. Okay, but we also ingest low entropy materials that we metabolize, and so in that sense we're power plants, and that's why we stay warm. That's why we have heat. So our entire existence as biological organisms is manipulating entropy, on the one hand trying to reduce it, and then on the other hand ingesting low sources of entropy and metabolizing them, combusting them, and getting energy out of it. So that's what a heat engine does. The refrigerator is the opposite of a heat engine. This is how we work. Now, I don't think we have so much of that instinct of what's going on in our bodies, but we see entropy around us all the time. We know inherently, I think a chimpanzee knows, that arranging things in a particular way takes effort and is unusual and is deserving of respect and awe because it took effort. And I told you before my analogy of the sorrow that we feel when something that has been artfully arranged then dissolves. So my favorite example is the 4,000-year-old vase, which has somehow defied entropy for thousands of years by maintaining its high level of organization. It has not dispersed. It has not degraded. It's been lucky. And then somebody drops it. Oh, my God, we feel horrified at this instinctively because we know how unusual it is for complex systems to survive over such long periods of time. And this is the same as the sorrow we feel when a living organism dies. You know, this was a highly ordered system, and now it's going to decay, it's going to disperse. Information is being lost. All the effort that went into creating that organism is now, it's been lost. It's no longer useful to us, and so on. So I think as we go through life, even as children, we understand that the inexorable pressures of entropy and everything that we must do in order to overcome and withstand them.
So it's a maybe less poetic or maybe more poetic way to talk about, say, the Twin Towers, right? Putting aside the loss of human life on 9/11, they were an architectural achievement. They took enormous amounts of effort to build, and they were destroyed. There's something sad about that, independent of the human life that was lost, which, of course, is also the same point. But I guess on the other hand, tell me what you think of this. I heard you say on one of your talks that that you're the product of maybe, was it 1 million supernova? Or was it 1,000?
Yeah.
It's a million?
It's 1 million. Mm-hmm. Yeah.
So, and what you meant by that was that there were elements produced in supernovas in the past that created the elements that allowed life to be created here on Earth, that eventually collected themselves in ways we don't fully understand into various organisms and then higher forms of life, a very anti-entropy experience as they got more and more complex. I think we're more complex in some sense than an amoeba. I assume we are. And yet, so when we die, even if whether we leave children or not is one question, but there's also just our molecules are not going to go away. They're preserved. It's true that the form of them will be different, right? But is there any comfort there for you?
No. If my molecules just disperse and don't reorganize into something interesting, now we're getting at, I think, the core question: what is valuable? What is interesting? What should we try to preserve? And I am not a religious person. And I think that we have a whole set of moral values that are kind of practical, that aid and abet and underlie our business plan, so to speak, our business plan being our strategy for surviving as an individual and procreating. But there's a bigger yearning, I think, that human beings understand, and really is an admiration for the organized, creatively organized structure. This is why we admire a beautiful scene, a beautiful painting, why we would feel awe, as I did when I watched the Chinese at the opening Olympic ceremony, the unbelievably synchronized, intricate movements that they had programmed there. We know intuitively how difficult it is to do those things. We respect it because it requires our effort, and our effort is in short supply. So, this is why it's important to know whether Earth is rare or not, because my analogy is beautiful places on Earth. My favorite is Yosemite.
One of my top five.
If somebody told me that Yosemite had been purchased by a developer, had been paved over, was now an airport and some hotels, I would feel outraged. I would feel a huge loss, because I understand intuitively that Yosemite is a very lucky thing to have existed in the first place. If Earth is rare, it's the same thing. Earth is a very lucky, rare place where wonderful things can happen. You can't have life like this on Jupiter. Jupiter doesn't support the creation of low entropy enclaves that we call intelligent life. And the number of places in the universe where this can happen might be incredibly small. And we would respect that as human beings. We would even worship that as human beings, and maybe develop the will to preserve, just as we've developed the will to preserve Yosemite.
I guess I have a couple thoughts. I don't think the amount of work, it's kind of for those students of the history of economic thought, there used to be something called the labor theory of value, which said the value of something comes from how much work gets put into it. That theory it's in Marx. It was rejected because if I spend hours tying a giant knot versus hours creating a magnificent new vehicle to travel in, say, or a new phone, some new gadget, the gadget's more valuable, even though if it had fewer hours, that the hours alone are not sufficient. Now, I can understand some of the poetry you feel for that. There's an aesthetic beauty in it, but certainly value is not solely the overcoming of entropy. It also has to have its implications for human flourishing, well-being, curing. Best example, the vaccine against COVID might have taken fewer hours than it took to organize the opening ceremony of the Olympics. Probably did, actually. You could define it differently because you could talk about what was necessary to get to that point, and it gets complicated. But just at some level, that's true. And I don't think they're equally valuable. I don't think the opening ceremony is more valuable. So I think that. So I'm curious, do you agree or disagree?
I probably disagree. Because
why?
Because at the outset, you put human beings into the equation, and whether they would personally and individually benefit from some activity. So I don't think that
you don't want to do that?
No, I don't necessarily want to do that. Because I don't think that human beings will last forever. And yet I would like to think that Earth will continue as a font of creativity. It's really the environment that I'm interested in and the circumstances that give rise to ever greater complexity and organization. And I don't think it has necessarily anything to do with human beings per se, although human beings at the moment are kind of the acme instantiation of that process. There might be something further in future.
Now I'm really mystified. So let me challenge you on one level, then a second. So the Nazi genocide of the 1940s of the Jews and some others, but mostly Jews, was very organized. They were really good at making the trains run on time and to make sure the trains were used with incredible efficiency. The Gulag of Stalin was an enormous undertaking. He had a number of projects in that. It was slave labor, building giant canals and other things that were inhuman, but were very anti-entropy, right? He built some incredible things. Many dictators have built incredible things with slave labor. Are you going to say that those are like admirable because they reduced entropy?
In and of themselves, they are, but they violated other moral norms. So I haven't really discussed my entire moral picture.
I think we need the rest of it.
Right, which is more normal and 99.9% synchronized with your view. I think in terms of value on two levels, on the low level, which is the immediate one, we have a set of moral codes which were developed to help us thrive in relation not only to our environment, to each other. And those are the codes that Stalin and the Nazis violated, and that's a horrible thing that they did. But that by itself isn't enough to help us plan for the future. There's nothing in those moral codes that would encourage us to value the future. Many people have said that a basis of morality is a transaction, that moral codes are basically transactional. How do we have a transaction with the future? What can the future give us today? That's the question I'm asking myself.
Okay, let's turn to that. But before we do, I just want to raise one last question about what you said before. Why do you care? Why would you care about whether, we can think of a lot of really unpleasant outcomes for the Earth: nuclear war, climate change that heats the planet through human error, volcanism that you talked about, bad turns of events, that come along, the asteroid that's bigger than the city of New York, and just it can't be tapped and moved away. So what? So the Earth gets destroyed and the universe loses a little bit of anti-entropy in this little corner of the Milky Way. Why would you care?
I think that's the central question. And the fact is, I think we do care, and I'm trying to figure out why we care. At the beginnings of many of my talks, I take an audience poll, and I ask people, take this as a given. Assume 1,000 years from now, the Earth is a smoking ruin. It's not hospitable for higher level, maybe microbes, but nothing bigger. And it's our fault. This is the key point. Our generation didn't do the whole damage, but set the stage for this terrible or this outcome. Is this good, bad, or you don't know, or you don't care? 95% of the people in the audience say it's bad. Why do they say that?
It's a deep question.
Yes, this is exactly the question. And I think it's because people respect the Earth as a miraculous vehicle for reducing entropy. And the loss of that was my hypothesis, that capability had gone away, is an inexpressible sadness and is to be avoided. And the question is, how much effort and cost are we willing to put in to taking actions that will avoid it? That's the question. But people say it's bad, but how bad?
But Alan Lightman on this program said, gives the analogy of the ant colony that flourishes for 400 years. Somehow this colony creates language and music and is very creative. And then a big storm comes along and washes it away. It has this unbelievable run for an ant colony of 400 years or 40 years or 4 years. Any of those would be impressive if they had a symphony or two. And he says, we're just in a big ant colony. We're all going to be, the sun's going to go out. We might flee to another star, but it's limited, and it's all just a matter of time. Now, I don't agree with that, or agree is not the right word. I don't see it the same way he sees it. But how do you answer that? Because you seem to have a different perspective.
I think I'd like to think that it can be avoided if we're clever. But this is why
we can't regenerate the sun, right? Which part could be avoided?
We would have to flee to another star. I agree with that. But I think
it's just
that's
a matter
desirable.
of time. But then, okay, maybe. But
yes.
So what? Still, then that star will go out. Eventually, we'll run out of stars, and the whole thing will just be a meaningless thing. That's.
I would say that you have pinpointed the central question for me that I am grappling with.
Okay.
And I still feel that as a human being, I feel it is sad that our run is cut off, especially due to our own thoughtless actions. I mean, the sun is one thing. We don't have to take responsibility for that. But we are responsible for Earth now.
So let's turn to the economics. Finally,
yeah.
We're only an hour into the conversation or so.
Okay.
So you challenged me when we first talked off the air to imagine an economy a million years from now. Before I give you my response to that, which has evolved since we first talked a little bit, why don't you tell me why we need to worry about it? Talk about growth and what concerns you.
Well, a million years is 40,000 generations. If you look at the recent history of world GDP, it's roughly doubling per generation. That's roughly a 3% growth, something like that.
Yeah.
So how big is that number if growth were to continue for 40,000 generations? I just did it before this conversation, got out my calculator. It's 10 with 500 zeros. Okay, so it's impossible.
Big number. It's a big number.
Yeah, it's not 10 to the 17, but it's large anyway. Okay, so the point is that that if our present economy is predicated on growth, and I'd like to know your opinion on that, then it can't continue very much longer. We're reaching the boundaries of the planets. Many people are saying this. We could grow for a long time, but we can't grow much further. So we have to figure out how we're going to be truly sustainable. Truly sustainable is zero growth. So I'm worried about, in the pretty near term, not a million years, but on the order of decades, I'm worried about things like bank accounts. How can I get interest on a bank account in an economy that's not growing? How can Harvard run on its endowment? Why will its endowment pay it anything if the economy isn't growing? Are we in for imminent social collapse when these economic institutions, which we take for granted, start to fail because growth fails? I'm asking those questions. What do you think?
Well, I think there's a couple questions. There's a lot of questions there. To back up to the beginning, I don't think our economy is predicated on growth. Because no one's in charge of it. I think it's really important to remember that. No one has a plan. There are people who talk about what they think will happen in a year or 5 years or 10 years, but it's not planned. So it's not predicated, I don't think is the right way to think about it. What is true is that for a long, long time, not long by your standards as an astronomer, but by our lifetime standards, over our lifetime, growth has been we've been very blessed, fortunate to have growth, which has many pluses, has some minuses, but many pluses. What has sustained that? And I think there's two questions to think about. One is it decades or is it centuries before we start to press against the limits of the planet? I think that's a very open question. The deeper intellectual question for me is how might we cope with whatever comes in the wake of that reset when growth is not available. So I want to talk a little bit about that, give you my take on it, and then you can respond. The reason I say it's not obviously true that growth will eventually have to end. And by the way, it's easy to have zero growth. We can just kill off everybody. And I say that because, it reminds me when people say, how do we reduce the risk of, say, how do we make airlines safer? That's easy. Ban air travel. The reason we don't ban air travel is because many of us have decided, not everybody, that the risk of dying in an airplane is a risk we're taking for the return of being able to get to places we wouldn't otherwise easily get to. That's true of many, many things we do. Car travel is even more dangerous than airline travel, though we don't always think of it that way. Things we eat are dangerous. We take risks all the time. And we generally decide, that they're worth it or not. If we said, I don't want any risk. I think risk is bad. We'd have to, sit by the campfire and not move or lay in bed all day. And even then, of course, you're going to be at risk of all kinds of things because you're not moving. So I think it's an illusion to think, I don't think the goal should be zero growth. It might even be negative growth, depending on what your values are and what you think is to be cared about. And maybe we'll get to that. But I think if we just get away from those deepest of philosophical questions, and we just ask the question, how should we deal with this? Let's pretend you're right. Let's assume that you're right. I have one more thing to say, actually, which is that, what is a resource? This is something I learned from Don Boudreau, longtime guest on the program, former colleague, still friend of mine, who channels Julian Simon the economist. What is a resource is not easily defined. Crude oil was not a resource in 1600. It was a nuisance. So some of the things that we call nothing today might become resources. Other things that are resources today we might decide we don't need because there's better ways of achieving them, of the uses we get from them now in other ways. The one resource that is not finite is our creativity. The question is it imaginable that our human creativity, our productivity, which has been unleashed over the last few hundred years in unimaginable ways, whether that could overcome those the finiteness of those elements. It's hard to say to me. I'm agnostic about it. I wouldn't say that because the Earth is a physically finite place. That's undeniable. Although I could say, that no, I won't. I was thinking about the shoreline, and I always love that paradox that the shoreline, if you take enough detail, you can make it long as you want. But there's something kind of intuitive about the way we use resources too. So, is it possible that a drop of oil could power the entire energy needs of the planet, and then maybe eventually a half a drop, and then a quarter of a drop? It seems unlikely, but it's not impossible that we could learn of ways to use oil. And then if we couldn't use oil, after a while, as it got more scarce, the price would go up. That would encourage people to look for other things. And that process of innovation steered by prices and scarcity is what has worked for the last few hundred years. Now, you're suggesting there might come a future where that wouldn't work anymore because everything would, quote, I think, be used up. Is that a fair way to characterize what you're worried about?
So it seems to me as though you're asking the wrong question. Somehow you've focused on the availability of energy. Energy isn't the issue. There's a lot of energy reaching the Earth from the sun. We can put out acres of photovoltaics and get a lot of energy. I think that would just make the problem worse. There are other issues. There's the problem of pollution, and there's the problem of mining. That is to say, exploiting other low entropy deposits that are not renewable. So, in some sense, finding huge, copious supplies of energy that would be adequate to support our enormous economic activities. Our economic activities, of and by themselves, are creating problems. And I return to the question of entropy because this is central to our problem. Our problem isn't energy availability. It's a problem of increasing entropy here on Earth by mining. I mentioned that. And also by creating dispersed pollution, which is like waste heat from our refrigerator.
Sure, but I think we produce. My impression is we are. I'll take an example. I don't know how this fits in with entropy. The amount of number of trees in the United States, I think, is increasing over the last 50 years. Or a lot of things like that. There are a lot of things we do badly because we don't have good property rights, like fish stocks. Fish stocks are declining badly because no one owns the ocean. Stuff that's owned and protected tends to be doing pretty well. Air is cleaner in the United States than it was 50 years ago. Much less pollution. Why are you so? In fact, we're getting better and better at producing. I mean, pollution is an example of inefficiency, right? Pollution is that heat coming out of the refrigerator, and the better we can produce things more effectively and use things without waste, which we have an economic incentive to do, we're going to make less pollution over time, unless, we forget how to do stuff or can't innovate. I'm not as worried as you are, I think.
Yeah. So how do you think we'll be set for copper 500 years from now?
I think, I'll give you, I don't know if we'll need it. I doubt it. I mean, there'll be less of it underneath the Earth's surface. Copper is really valuable. So, copper is something that's recycled without government mandate. People strip steel copper from abandoned houses because it's worth it. So copper's valuable. It still gets thrown away. It still gets, has to be reused with additional energy. But right. Maybe in 500 years we'll be out of copper. I don't think we'll use the last ounce of it. As it gets rarer and rarer, it'll get more and more expensive as it gets harder and harder to find and dig up. And that'll encourage us to find substitutes. That's been the history of the last 350 years of human experience. The things that are rare.
There really isn't any substitute for copper. There's no substitute for water, for example. We already use
that. I agree with.
But I've lost the track of your question. The question, are you defending some sort of future that's feasible and asking me why I don't believe in it?
No, I'm trying to make you feel better about how the future is going to unfold. I've got two things to I want to make you feel better about you're worried about the future. You think we ought to be proactive and take steps to put in place systems and alternative ways of organizing economic activity that are better than the ones that we have now. That's the way I take your original question. And
that's a near-term issue with me, not a million-year issue.
Well, it's both. It's clearly both, right? Yeah.
Both, yes.
So, I have two thoughts. One is to comfort you that the short-term prognosis is better than you might think, and the second is to make you worry more about your alternative to mine, which would be a more organized effort to rearrange things. So, on the first count, I think the role of prices are pretty extraordinary, although I'm a little worried about in recent months in the face of COVID how badly we've had to deal with shortages that normally I would have thought would be eliminated by changing prices, which suggests to me that we don't really like the way the price system works and we might not be willing to take its signals and use them. But in general, things that get scarce get expensive. That encourages their conservation and encourages the search for alternatives. Yes, there may be no substitute for copper, but as copper gets more and more expensive, we'll look for different ways to do the things that copper does. It's in people's incentive. We don't need a plan. It'll happen naturally if we let the prices rise and don't artificially try to stop them. We may not like the social consequences of those higher prices. Could be some people who can't afford to pay for copper things. In the meanwhile, in the short run, those are serious social issues I wouldn't say are irrelevant. But just the question of how will we cope with the ever smaller amount of copper available under the surface of the Earth doesn't strike me as a apocalyptic crisis.
I think that's would be a mistake to be so sanguine, because it's one way of dealing with the copper shortage is you now mine lower quality ores, which is what we're doing. That costs more energy, and so the return is lower. That's the problem as we deplete resources. Sure. And the long way of saying it is that we are using up the lowest entropy assets and going to somewhat higher end. Our standard of living will go down simply because it will take more effort and energy to get the stuff that we are living off of.
That assumes no change in our understanding of how to organize the resources that we already have and the resources we have yet to discover that may substitute for them. You would have said the same thing in 1973. People did. They said the amount of oil in the world is finite. We're going to run out soon. They picked a date, actually. I love this. They picked a date, and they said if we don't do something about it, we're going to have chaos, crises, famine, riots in the streets. They didn't see two things. They didn't see the fracking revolution. That's the least interesting part to me. But the more important thing they didn't see is they didn't see the ways that we would figure out to use energy more effectively. They certainly, right, you're optimistic about photovoltaic alternatives to petroleum. Even until recently, people say, oh, it's too expensive. It can't scale. I don't know. I don't know what our options will be. But let's pretend you're right. Let me grant you your.
Let's be clear about what, before saying I'm right, what am I right about?
Let's say you're right that the finitude of various resources, ore and other things, And I should just say, we had Paul Sabin on this program as a guest talking about the debate between Julian Simon and Paul Ehrlich over whether we were running out of stuff and what the consequences would be. And they made a bet, and the bet was contingent on the price of these resources, and the prices got lower, not higher. And so Julian Simon won the bet, and Paul Ehrlich lost. And you could say, well, that was then. Eventually, there will be a time when that constraint will kick in. So that's the part I want to concede might be true.
Okay.
The reason I think one should be. I don't think you should be convinced of that, because I think there is the opportunity for human beings to find ways to deal with substitutes that we have done successfully for hundreds of years. But maybe that run will end because of as we get increasingly into the most expensive, the hardest to reach ores and other resources, perhaps it will become so expensive. The amount of energy needed will become so high that we won't find newer ways to do it. And as we have in the past, we won't find better or more effective ways to find out where the oil is, and et cetera, or the ore. And so eventually we'll have to run up against these constraints. Maybe it's, I think your best argument is, okay, maybe it's not the next 20 years. Maybe it's not the next 100. Maybe it's 1,000 years from now. Maybe it's 100,000 years from now. But surely, at some point, we will run up against the finiteness of the Earth. And we don't know what population is going to be then. There's no way of knowing. Maybe we'll have found ways to live together in smaller amounts, or maybe we won't. But that could make the problem worse easily. So eventually, we'd have to deal with it. So the question is, how do we deal with it? What is the structure? What would be the governance, the process to deal with that? What you think is a reality, and I think is maybe a reality. So I'll concede that. So that's the toughest question for me.
Yes.
Yeah. The ingenuity of human beings to cope with what we might call economic challenges is really pretty impressive. Will it run out? Perhaps. Fine. Let's say it will. What should we be doing in the meanwhile? That's what I think is your real question, right?
That's my real question. And if you're hoping to get an answer from me about how we should live then, I don't have one. My goal is to get us talking and thinking about it, to generate scenarios for what a future would look like. And I would start by trying to enunciate some boundary conditions.
Go ahead.
And the boundary conditions, first of all, would be a resource consumption of all kinds and waste production on the other. I'm just thinking of the economy as one of these heat engines. Stuff comes in and stuff goes out. And understanding the laws of entropy and energy, we can actually, a physicist could sit down and write down those boundary conditions. I can't do it right now, but I think it can be done. Then the next thing you have to do is you have to decide what you want. And that's the value question. So within some constraint of resources and waste production, you could probably have more people living at very low levels versus a smaller number of people living at higher levels. What do people want? This is where I think the discussion of values comes in, and you see it at that level has nothing to do with our morality that we were on the subject of before, namely how we treat each other. This is a bigger question, and this is why I'm very interested in the value of Earth, if it has one, of cradling and nurturing complexity, which is the more interesting situation. A bunch of people living hard scrabble off the land, larger numbers, but consuming per capita less, versus a much more complex civilization, but with fewer people and net resource consumption the same. We never talk about things like this. This has never been a discussion, to my knowledge, that any human beings have ever had.
Well, I think it gets talked a lot about in philosophy classes, but I don't think they come to any answers, right? One answer, I find it unattractive is to invoke utilitarian principle that it's the greatest good for the greatest number of people.
What is good?
Well, I have a lot of problems with it, but I think if Peter Singer were here, he would say the right number of people, we should try to maximize the total amount of happiness that is sustained on the earth. I don't think that's a measurable question. I think it's a meaningless statement. It has no content and doesn't. I don't mean to criticize Peter Singer. Maybe he'd come up with something more creative than that. I'm not talking about the ultimate straw man, right? I don't like utilitarianism, and here I am criticizing the most prominent utilitarian I know's plan for the future that he hasn't articulated in response to your question. But I think people have tried to answer your question. What's the good life? They might have preferences over those two worlds, either for themselves or their children. You don't agree?
I don't think they're answering it the right way.
Go ahead.
They're focusing on one's immediate happiness. Do I have enough to eat? Am I warm? And so on. Missing the bigger question of the bigger issue of value. What is lost to the universe, if anything, if a higher level of civilization ceases to exist on this planet? I think something will be lost, because I think the planet as a device for creating complexity and interest is something that we value as human beings. Remember that saying, how are you going to keep them down on the farm after they've seen Paris?
Yep.
We as human beings love innovation. We love change. We love complexity. We admire all of these things. And that's not happiness. It's something different.
Oh, it is
something different. And probably using our expressions for entropy and information probably could be quantified. And I would submit that a large number of people living very simply off the land would have a lower quotient in that index than a smaller number of people living a more complex life, with each individual having a larger amount of energy and resources at their command.
Sandy, you're not going to like this, but
okay,
you sound a little like God, right?
I am.
Right. Who's this thing? What's this thing out here somehow separate from you and me and the earth that feels sad when the earth disappears or when there's less civilization? Who's feeling this loss? Right? I mean, it sounds like a hardscrabble life for a lot of people living near a subsistence level. That sounds horrible, but I'm using very traditional morality on that. What else would you use? Who's this creature, this entity that's feeling sadness that there's no Eiffel Tower?
There's no external creature feeling sadness. It's us feeling the sadness. It's us imagining. It's we imagining future scenarios and seeing some that are barren and some that are fruitful. By way of our innate way of judging things. And our respect
so I'm
for...
You go ahead.
Okay.
Sorry. No, go ahead.
I was just going to say, I think our respect for... I think our moral system, our day-to-day moral system, is a product of evolution. Just, came out of what chimpanzees do. They have all the basic essences of it, as far as I'm concerned. I'm talking about a higher level of value, which I think is also born out of evolution, because we understand intuitively, as creatures who observe things on this planet, how hard it is to create organization and complexity. We respect that, and we value Earth as a place where that can happen.
Do you feel that way independently of the people who are going to inherit that Earth, right? The next 40,000 generations? I mean...
Well... We know, look, a species only lasts for 1 million years or so. So to speak of people over long periods of time, you don't mean that. You mean our descendants somehow. Beings that descended as a result of cause and effect in a chain, of which we are the beginnings now and they are the result. I don't know. They might be machines. I doubt that.
Well, let's go there. No, let's go there. let's suppose they are machines. Let's suppose we create some artificial intelligence in a box that expands and destroys all of humanity to feed itself, which some people are worried about. Very smart people. We've had some of them on the program. Would that make you? That would make you happy, sad, irrelevant? You're saying that doesn't matter? They're just a different thing that we were the ancestors of?
I pretty much would agree with that. Yes.
Not quite sure what to do with that. Interesting. I disagree, but that's just a matter of, you could argue it's just a matter of taste.
You sort of built in the result you wanted from me by saying that they destroyed humanity. Let me put it another way.
Okay.
Supposing humanity sees that the long-term solutions to problems of pollution resource generation is if we switch from being biological entities to machine entities, that there would be somehow an advantage to Earth as a creative by making this switch. And it's voluntary, and we designed it, and they're our descendants now. That's fine. That's great. You sort of built in the bad thing.
No, it's still horrifying. No. I don't need to build in the bad thing. I think it's horrifying. I have no interest in that future. Absolutely. It comes back to my point before. Who's excited about the Earth being this great generator of creativity and order when it's just a bunch of machines? I don't get it. Help me here.
I'm taking it for granted.
It's one of the darkest futures I can think of.
Really?
Yeah, I really, totally. Now, I try to be a little bit self-aware. I understand that as a person who's religious, that this is part of it. But I have a feeling a lot of non-religious people also would be uncomfortable with that. I don't know.
Well, they'd be sentient.
Maybe. It's unclear.
Take it as part of my hypothesis that they are.
They have consciousness? Okay? Do they have consciousness? That's what you mean?
And they have feelings. They have emotions. That's very important.
Okay, so I get it. I get it now.
I'm more and more. This is kind of a down way to end the interview. I'm really more and more thinking that we are prisoners of entropy, and that the generation of waste entropy and the consumption of irreplaceable low entropy assets on Earth will be our undoing eventually. And then, returning to your question, what does it matter on the time scale? If it's short, if we go out in a blaze of glory, why not? Why prolong things? Why keep matters moving? I guess I would say that as long as we're functioning, there's always the possibility of solving new problems, moving to another planet, whatever. I mean, the machine is moving. If we commit suicide here on this planet, it's over. And that saddens me. I would not like to see that happen.
But the reason it saddens you is not the reason it would sadden me too. I don't think we're headed in that direction, although politics around the world gives me pause right now at this particular moment. But what I'm having trouble with for the last 15 minutes of our conversation is I don't understand why that makes you sad. Is it to make you sad for the Earth?
Yes.
Why do you care about the Earth independently? That comes back to my point about the external observer, God, whatever. You care about it because you're looking ahead to that this is a precious environment that we are squandering. Is that a fair way to say it?
Yes. That's right. It's one of the very few places in the universe where processes can operate to create low entropy enclaves. Most of the universe isn't like that. And only in such enclaves can interesting things happen.
Just trying to understand.
Otherwise, just all the distinctions, everything comes into thermodynamic equilibrium. We have heat death, that kind of thing. And it's not interesting. I keep using that word for lack of anything better.
But it's going to come after you're gone. Why do you care?
I think everybody lives for the future. You're living for the future. This is again part of the human organism. We are all oriented towards the future. The problem is we're oriented towards futures that are rather near term, probably associated with our direct progeny. It's hard for us to have an intimate connection with the far future. And that's the basic challenge in trying to plan for the future of Earth. I've thought about it now, and I'm trying to figure out why I do feel this urge to preserve Earth as a creative environment. All I can say is when I talk to other people, they have the same urge. It all depends on how strongly we feel that urge, because we have to make sacrifices today or changes in order to preserve Earth long term. Are we willing to do that?
What we didn't get to is that it's not enough to want to make changes or to make sacrifices. You have to make sacrifices that lead you to an outcome you're going to like. My worry is that we don't have a process to make those decisions.
Yeah.
Go ahead.
I worry that there's an outcome. There's no outcome that we like, because I think we're all impressed by the status quo, a planet with an enormous economy, many things going on. It's fascinating. It's a miracle. There's no question about it. But when we look at the current rate of resource consumption and waste production, I feel that can't go on very much longer. And so the future, a million years from now, is smaller in order to be sustainable. It's much smaller. I'd like to know how much smaller. What's the carrying capacity for an interesting civilization over millions of years? We don't know that.
Can't be answered.
I'd like to know that.
Can't be answered. And it can't be answered for the same reason it couldn't have been answered when the first Neanderthal wandered out of the cave and with a stick and hit a creature and had something to eat. I mean, just think about those changes. That extraordinary, civilization's an unbelievable transformation of the. You look at the surface of the Earth. I mean, in one sense, it's trivial because they're just little bumps. They're not very impressive, but we've certainly found some unexpected ways to do things. Can we not find those again down the road?
No, because I think we know much better the laws of physics, including the laws of energy and entropy. The caveman didn't know anything about those things, and that was all new territory to be explored. We know much more about those things now.
My guest today has been Sandra Faber. Sandy, thanks for being part of EconTalk.
Thank you.
This is EconTalk, part of the Library of Economics and Liberty. For more EconTalk, go to econtalk.org, where you can also comment on today's podcast and find links and readings related to today's conversation. The sound engineer for EconTalk is Rich Goyette. I'm your host, Russ Roberts. Thanks for listening. Talk to you on Monday.